Okay, so I work at Netronome as well. We have developed a hardware offload for eBPF, and I sort of wanted to present sort of a retrospective on BPF hardware offloads and why it makes sense, and why it makes more and more sense as we work on this technology to us. So the motivation for the talk is the hardware platforms obviously get more and more complex, and our realization is that a lot of the hardware platforms that we use today as I/O devices for networking or storage, they all contain small RISC processors effectively inside, and for some of those RISC processors we already have JITs inside the kernel. And the entire idea of the talk is how to make it possible for the kernel to add basically hooks inside those devices, because we already have JITs for architectures like ARM, or maybe one day we'll have a RISC-V JIT for eBPF, and if the device is running as a RISC-V or ARM device, the kernel already has the JIT, so all we need is a little bit of firmware glue, and we can start installing BPF programs inside the hardware. When we started, we mostly worked on networking devices. That's what our company makes, and our purpose was to open the networking devices and make it possible for people to integrate their BPF logic inside the networking device, which opens a lot of different possibilities. Performance is just one of the things, but a lot of things become possible when people get a real view inside the hardware. So when we look at evolution of hardware and how it gets opened, it usually starts pretty much the same way that BPF started inside the kernel. There's usually a fixed pipeline of some sort, and then there's little windows of programmability that open up within that hardware. And this is sort of a good parallel for how BPF started inside the kernel. We started with this fixed networking pipeline, and then different hooks started appearing, and today we can attach our BPF programs to sockets and do all sort of crazy stuff, and basically define the processing pipeline entirely in BPF. But and we hope that the same thing will happen for devices, where we start today when there's one hook where we can attach our BPF program inside the device, but hopefully one day we will be able to define the entire processing of the hardware device using just BPF programs from start to finish. And then there's a lot of other parallels which become apparent when one looks at BPF and how it relates to the hardware and how it relates to the kernel stuff. So one of the goals of designing kernel APIs is to make sure that the implementation underneath and all the mechanisms that we use inside the kernel can change, and the API remains stable. And when we think about the hardware and how we design APIs for hardware devices, we sort of want the same thing, because we want to be able to use the same APIs across different vendors, which effectively means we want to use the same API regardless of the actual implementation. So that's another parallel. And yet another thing that's sort of important from a hardware perspective is that the BPF as a device programming API has a very well-defined semantics. So we heard the talk, for those of us who are in the networking track, from Jesse yesterday about how we have APIs in the networking stack for all sorts of things, but depending on the driver that one runs, the API will actually do a slightly different thing. And in the BPF world, that shouldn't really happen, because we know what the BPF program is supposed to do, and how it's the definition of BPF is effectively down to the BPF interpreter in the hardware, in the kernel. And if something doesn't work exactly like the interpreter in the kernel would, that means it's incorrect. So we have a very well-defined execution environment and a very well-defined user API, and that is nice when we want to effectively provide portability across different hardware platforms. So I started by looking at this and sort of went from the perspective of what hardware-specific IRs, intermediate representations for programming devices there are, and most of the ones that we have today are related to graphics. We also have P4 for programming switch ASICs, and there's also things like VHDL, which are kind of very close and hard to analyze. But looking at mostly the graphic stuff and how it compares to BPF, there are some parallels. So one of the things that is important for all the languages that are hardware specific is to be able to make use of all the hardware blocks, like the ASIC logic that accelerates the processing, and we have that in BPF in form of helper calls and maps. So the BPF sort of works in a sense in the same way as the hardware offload languages. The other thing that is similar is that, as I said, all those languages are sort of starting from the point where the processing pipeline is defined, and then we have little islands of programmability, with the exception of P4, which started with like we can define the entire pipeline, but they worked backwards, and today they also mostly like focusing on the little islands of programmability. There are differences though. The biggest difference that is immediately obvious is that most of the graphics processing APIs have the data types and all the data definition inside the AR itself. So that's something that hopefully we'll get with BPF soon as well, thanks to BTF. But yeah, that's definitely something that is there from in the other languages, and right now we don't have that in eBPF. And the other thing that sort of becomes obvious, and it also is like very obvious to us who work on the hardware offload, is that people compare P4 to eBPF, which is not comparing to apples at all, because P4 is like a very high level language, and the IR that P4 generates and all the graphic languages generate as well, the purpose of it is to not lose any information at all from the program that the user wrote. So you need to have like an entire full compiler in the user space to get that stuff lowered into the machine representation, and BPF is kind of the opposite. The BPF language, the eBPF that gets loaded into the kernel is supposed to be really easy to generate machine code for. So there's definitely that fundamental difference there. And now I'll talk a little bit of the experiments that I did. So if you want to offload eBPF into a hardware device, we can like think about it in two ways. One of them is to try to reuse the kernel existing infrastructure and all the JITs that we already have in the kernel. And the other one is to just take the eBPF program and pass it on without any modifications to the firmware, and let the firmware do all the work. And I think the first option, where we do the compilation in the kernel, is a lot more interesting, because it should make it easier for people to start playing with this and for vendors to provide this capability. So if we are able to make it easy for them, perhaps there will be more vendors trying to provide this capability. And this is sort of the slide that tries to explain that graphically. Right now we have the eBPF subsystem, and then when we compile a given architecture, then we will get a JIT for that single architecture. But we have in the kernel tree effectively JITs for all the other architectures. So if we separate the JITs from the architectural code enough, we should be able to have the code gen for every architecture compiled into our kernel. And then if the device is running some standard architecture, like it has MIPS cores or ARM cores, we should be able to, with very minimal firmware integration, just move a program that's compiled on the x86 host for ARM into the device and execute it there. So the stacked colorful sort of thing on the left is sort of exploded view of the verifier and things it does. So sort of to look step by step at all the things that the verifier does and things that we can reuse. And a lot of stuff just works without any modifications, as you can see on the far left. There's two things that we would most likely have to like add to the verifier to make it possible to generate code for effectively a different execution environment. That's the we need to provide the addresses of the helpers and remove all the kernel-specific prologues. And with that in place, it should be fairly easy for a device which can fake a kernel execution environment, just the data structures, to have a program loaded into the firmware and sort of execute within the device context. And we can obviously like modify more things and provide more flexibility, but that would be a good starting point for people to basically be able to, with minimal effort, to start opening up their hardware and their firmware implementation. So I did a quick POC of this sort of way of thinking. I took an x86 kernel and I pulled out the ARM64, the AR64 JIT compiler and put it in a different place so it would get compiled on x86 with a few like header hacks and stuff, and attach that to the netdevsim, the fake device we have in networking to test various things, BPF offload amongst them. And so I would have a BPF program loaded on an x86 host, then netdevsim would invoke an ARM64 JIT, the code gen, and then I would output that code into a debugfs file, which would then get loaded into QEMU, as ARC64 QEMU, and then it would execute there, and it was like a day of work, maybe day and a half, and I had the x86 kernel effectively faking execution of an ARM device. And that's pretty much what I wanted to present.
Comments, feedback? Okay.
Hello. I was just wondering whether this is really interesting for when you're looking at things like ARM or MIPS or all these kinds of processing cores. But did you give it any thought about what happens when you start looking at potentially devices like sort of standard NICs or TCAMs, that kind of thing? If there's a way that we could maybe offload some of the simple functionality which they can use via something like a JIT.
Yeah, I mean, this is kind of looking the opposite direction from going like full fixed pipeline into going fully programmable pipeline. So I don't think that helps for fixed pipeline people.
At one time, I don't know if it was a great idea, but we prototyped adding generics into the LLVM, and we would have a generic for the TCAM link, so that you could write it in your C code, and then the JIT would get passed all the way down to the JIT, and then you could load it into the hardware, so you'd have like a intrinsic. Sorry, maybe I said generic, but I meant intrinsic to do like the TCAM load or read, which I don't know. It worked, but it destroys sort of portability to software, so you would have to have some sort of backend for the software that the JIT could convert it to, right? Yeah. And then since then we've got a lot more maps, so maybe the maps sort of get rid of the need for that.
Yeah.
You could have.
It's interesting. All right.
Could you go back one slide? Do you see a possibility how we could integrate something like that into the test suite? Because a lot of times when we do JIT changes, I think we have x86, 64, ARM64, you guys are testing NFP, but sometimes, for example, MIPS, eBPF JIT or other things, it's really hard to test because we don't have really access to the device, right? So do you see something how we could automate that as well, and then make testing easier?
Yeah, I mean, we could do that here, I think. I mean, it's pretty easy also to attach like GDB or something to the QEMU process. So that also helps if you want to debug your BPF process, your BPF processing. So there's, yeah, it can help. But I mean, someone would have to commit and convert all the architectures.
Probably you. I would really love that. I like the idea. All right. Thank you very much.